Lesson 43, alpha, beta, and gamma decay. And once again, I recommend you go onto YouTube and watch just Google alpha, beta, gamma decay, watch a video on it. It will make it more interesting and relevant to you. You can read over these notes about Henri Becquerel and Marie and Pierre Curie. And then, but I'm just going to kind of go right into the meat of it. So in the last lesson, we said that bigger nucleuses are less stable. And here's a periodic table. And all these light blue ones, they're really quite stable. And then when you get into different colors, they get less and less stable. The greens are less stable, and the yellows are less stable than the greens, and so on and so on. And these purple ones over here are really unstable, and they decay really quickly because they have huge nucleuses, and therefore neutrons and protons can escape from the nucleus. And we know that if a proton escapes from the nucleus, then all of a sudden the element is not the element it was. So if I have, well, let's make it easy. If I have helium and one of those protons, now this is not going to happen because helium is a pretty stable atom, but if one of those protons happens to be ejected or leave the nucleus, then what have I got left? I've got hydrogen. Hydrogen 3, actually, because I got 3 nucleons. It's a hydrogen isotope, but the element has changed. It is no longer helium, it is hydrogen. So when we're talking about decay, in some form, most forms of decay, we're talking about a transmutation. A transmutation is when an element changes from one to the other. So let's do another quick example of that. Let's say I have oxygen. And again, I'm using really small ones which don't decay necessarily. So I have oxygen, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Nice stable oxygen atom. Now let's say that oxygen atom gives off an alpha particle, ejects an alpha particle from its nucleus. What is an alpha particle? Well, an alpha particle is a helium nucleus, 2 protons, 2 neutrons. So if, oh, I got one right there. So if this gets ejected from the nucleus, all of a sudden there's only now 6 protons in that nucleus. So all of a sudden we have a carbon. And as a matter of fact, there'll be, if I did 8 and 8, there'll be 6 and 6, so that will be a carbon 12. So all of a sudden that transmutates into carbon. And this is what decay is all about, radioactive decay. Okay, so let's go back up to here and discuss the types of decay. The most common one that we're going to discuss, well, the 2 most common are the first 2, alpha and beta. And I just discussed alpha decay. Alpha decay is when an element ejects basically a helium nucleus, 2 protons, 2 neutrons, or an alpha particle, and it transmutates into another atom, usually a more stable nucleus. The second one, actually, let's just go through this. So Ernest Rutherford and 3 others started studying radiation that was emitted by these elements. So they found these radioactive elements like polonium, uranium, thallium, actinium. I don't know if that they did all those ones, but polonium and they would have done. And they noticed that they were ejecting, they were transmutating into different elements. And so they found out there were 3 types of radioactive decay. There were alpha, and that's where a nucleus ejects an alpha particle or a helium nucleus. Then there's beta, and we'll talk about more beta and more in a minute. And then there's gamma. Now these 2 involve transmutation. So they become different elements, but gamma radiation does not. Gamma radiation is when it gives off, a substance gives off gamma radiation or gamma rays, in other words, EMR, and does not transmutate. It just gives off a very high frequency, high energy form of EMR that can be very damaging. And it discusses the effects of these types of radiation right here. So an alpha particle can barely pass through a single sheet of paper. It's deflected as a positive particle in magnetic field. A beta particle is negative, or they can be negative and positive, can pass through about 3 millimeters of aluminum, and it's deflected as a negative particle in the magnetic field. And then the gamma can pass through several centimeters of lead, and it's not deflected by magnetic fields because it doesn't have a charge. And then you should watch more videos on the radiation dangers, because when you go to the dentist and they take an x-ray, they put that big lead vest on you. Why is that? It's because you're being bombarded with radiation, which is not good. It makes your cells transmutate. Well, not transmutate, it makes your cells mutate. Something you don't want them to be. Here is a really good, this question appears on diploma exams, and it's you got a magnetic field and you got a source of radiation, and then you've got what would happen to each of the 3 types of radiation if they were emitted from that source. So you can see you can use your left and your right hand rules. For the alpha particle, you can use your right hand rule because it is positively charged, so your finger's going to point into the board, your thumb is going to point up, and therefore your palm is facing to the right, or to the left, So an alpha particle in that situation would be deflected to, or an alpha particle would be deflected to the left. If it was a beta negative, and when you see this symbol here, that means beta negative. You can use your left hand rule, fingers go into the page, thumb goes up, and that one is deflected to the right. And a gamma radiation has no charge, so it doesn't get deflected by a magnetic field. Okay, on to the description of each in more detail. This one I've discussed already, so we don't need to do it in a huge detail, but it basically says an alpha radiation is basically when a helium nucleus gets ejected from the nucleus, and therefore the element changes into something that has 2 less protons in it. Okay, and then we get onto this, the conservation of nucleons. The total number of nucleons must remain the same before and after a decay reaction. All right, so now we're going to get into decay reactions. And here's an example here. The iridium 186 isotope is known to go through alpha decays. Write out a decay equation that shows this process. So iridium, and it's 186, so it has 186 nucleons, and you would look on your periodic table and you would find out that iridium has an atomic number of 77. So it has 77 protons, and the rest are neutrons. And it said it goes to alpha decay. So we write an arrow, and it's going to eject an alpha particle from the nucleus. Therefore, there's going to be, so first of all, this is how we depict an alpha particle. Right, the alpha symbol, and then 2 protons, 4 nucleons, in other words, 2 protons and 2 neutrons. And then this is just a balancing act here. You just have to make sure the left side equals the right side because of the conservation of nucleons. You can't destroy or create nucleons. They must be conserved. So we've got a 77 here, and we've got a 2 here. What number must go right here? It's got to be 75. Because now we have 77 total on the left side, 77 total on the right side. What number goes at the top? Well, you got 168 and you got 4. What must this be? 164. Then we're going to go to our periodic table again, and we're going to find out that the element that has 75 protons is Re. I think it's rhenium. Sorry, I don't have my periodic table with me. So that's the element that it is transmutated into. And we do have names for all these. This is called the parent nucleus. This is obviously the alpha particle, and the resultant is the daughter nucleus. So you may see that terminology when you're dealing with alpha decay and beta decay. Okay, and continuing on. Well, something is missing here. So we're going to stop here and finish the second part of this in part 2.